So hello everyone, and welcome to this week's colloquium on the topic of climate change, mitigation, resilience, and adaptation. So last week you heard from William, Rachel, and Sam, who highlighted the role that we as scientists and current research plays in climate science and in responding to the climate crisis. We're excited to share with you today a snapshot of strategies and solutions being actively developed in order to address and work on the climate crisis. And this is part, of course, of the climate series. And so here is just another overview of all the talks that are part of this. And so we're just on the second week of this range of topics. So today we are very happy to welcome our 5 speakers, Julie, Ryan, Kevin, Idalia, and Greg, who will each give a 7-minute talk. And so because this is quite a short period, at the end of the session, we will have a combined question and discussion period. So please leave your questions for the end, or if you don't want to forget about them, feel free to write them in the chat and we can refer back to them later.
So climate solutions are complex and we need to work on many fronts and many timescales at the same time. This includes working with communities that have already been impacted by the climate crisis, prepare for immediate forces that are upon us, such as the recent Sumas Prairie floods, and set up systems to notify people during future disasters. We also need to lower emissions, make sustainable choices, and get green energy and new technology on board, as well as removing carbon dioxide from the atmosphere. Before we start today, I'd like to acknowledge that we are gathered virtually today at UBC, which is located on the traditional, ancestral, and unceded territory of the Musqueam people. Personally, I'm joining as a European settler and live and work on the lands of the Coast Salish peoples, including the Musqueam, Tsleil-Waututh, Stolo, and Squamish peoples. I would like to express my gratitude to be able to spend time and connect with this beautiful land. The topic that we're covering today is critically intertwined with this, as climate change impacts marginalized groups disproportionately. Thank you all for being here and listening. And without further ado, I'd like to hand it off to our first speaker, Julie.
Hello, good afternoon. I'm Julie. I'm calling today from unceded Squamish, Musqueam, and Tsleil-Waututh territories in North Vancouver, BC. I have a geological engineering background from UBC and a disaster risk management background as well. And I work as a science policy analyst with the Geological Survey of Canada at Natural Resources Canada. And next slide. So I'm today talking about flood risk. So I'm going to take a quick moment to talk about some recent events. So here's a second on Sumas. As most of us now know, Sumas Prairie was a lake around 100 years ago. The hydrology of Sumas Lake in the region was very well known. In November 2020, a report was published publicly that includes results from a detailed hydrological analysis of the area, a risk assessment, and an evaluation of mitigation options based on the risk assessment. So all to say, the flood event and its consequences were estimated and known before the recent events. And I am in no means pointing fingers or saying we should have done anything differently, but we're at the very earliest stages of looking back at this event and wondering what we can learn from this experience. One thing we can learn is that water flows downhill, even when downhill is north and across an international border. But also we can learn that the most sophisticated understanding of flood hazard doesn't necessarily lead to risk mitigation, resilience, or adaptation. So how can we ensure that that happens? Well, next slide. A big part of that is understanding the hazard. The flood in Sumas is one example of a flood hazard, and there are an infinite number of other ones, both riverine and related to coastal areas. And a huge one there is relative sea level rise. It's going to cause incredible changes to our coastlines within our lifespan. So understanding the hazard, that aspect of disaster risk reduction comes through the scientific process. It comes from researching and then applying that research to the natural environment. And the understanding that we have of hazards is, no matter how good we get, it's filled with gaps and uncertainties, but it's the best basis for rational decision-making that we had. But again, we had this, and we have this in many areas. Next slide. So there is more to disaster risk reduction than just understanding the hazard. Canada and British Columbia are signatories to the United Nations Sendai Framework for Disaster Risk Reduction. And if you study any sort of hazard or disasters, it is well worth a read. It boils down to 4 priorities for action: understanding disaster risk, strengthening disaster risk governance, investing in disaster risk reduction for resilience, and enhancing disaster preparedness for effective response and building back better. Researching and understanding hazard fits well as a component of that first priority, but to do effective disaster risk reduction, we need more than just an understanding of hazard. Next slide. In order to achieve that risk reduction, there's a collection of information needed, including that all-important piece of hazard that as geoscientists, we are very good at. We also need an understanding of impact and exposure, which can be quantitative or qualitative. We need to put that together in risk analysis, and then driven by community input and local context, this feeds into risk reduction decisions. Next slide. So what does this look like? Here's an example in practice. This is a coastal flood risk research project I'm working on as part of the Public Safety Geohazard Program at Natural Resources Canada. The project has the goal to develop and demonstrate best practices and tools in coastal flood risk assessment. Through 3 case studies, we've analyzed the hazard and worked with communities to build that into a risk assessment that they can use to make important decisions about their futures. And through the project, we've developed an open source flood risk assessment tool, informed marine coastal flood hazard assessment guidelines, and built hazard and risk knowledge in the communities that we're working with. And I'm gonna, next slide, focus in on the last step in the cycle, and that's risk reduction. So we've built our world. Here's an example of a built world with fairly high density development. We've actively reduced natural flood attenuation. We've placed infrastructure relatively close to water, because we all like those shoreline properties. And we've typically used a sophisticated system of flood protection measures with a defined upper design limit. So the way we've built our world, we haven't left ourselves a lot of easy risk reduction options. Next slide. The main options that we have are to protect our existing infrastructure, accommodate flooding through wet proofing or dry proofing measures, kind of learning to get our feet wet, or retreating. But all of these options come with significant costs, disruption, and social equity implications. Next slide. Speaking a bit more about protection, we have a long history of that here in BC. Protection seems to have been almost instinctual to many settlers who came, but this has created problems because providing flood protection measures such as dikes has been shown throughout history to intensify development behind the dike. And these dikes are fallible. There will always be an event that is bigger than the dike. And with climate change, those events are more and more likely. Upgrading dikes is estimated to cost in the billions of dollars for BC. And it's often the communities least able to afford or implement dike upgrade programs are some of the most vulnerable in some ways. Additionally, these typical protection measures are quote unquote hard infrastructure solutions, such as the one on the left, and it can have a devastating impact on ecosystems, especially coastal ones. So there's significant research and guidelines being done these days to develop nature-based solutions, such as the one seen on the right. Next slide is about accommodation. So there are technical physical accommodation strategies, but these can also be difficult to implement in our society of privately owned buildings and where we typically take reactive risk reduction measures rather than proactive. Accommodation strategies can also cause social equity challenges. Research is starting to show that in many areas that have experienced frequent recent flooding, especially coastal areas, climate gentrification is occurring, where higher risk properties become cheaper to purchase or rent, and therefore end up housing less economically wealthy populations who may have less capacity to rebuild their lives when the next flood event occurs. And the next slide is on retreat. It's also difficult to implement, especially as it's not currently supported by most funding programs. And it's an existential question for communities, especially those with limited area to retreat, such as reserve-based communities, or those which face other hazards in other areas. And I'm going to skip over the next slide on the decision-making process, just to say a quick thank you, and hopefully this gives you an idea about how flood hazard information is used for risk reduction. and how it's really important for those of us with a deep understanding of hazard to follow the discussion through the decision-making process and through really connecting with our communities. And coastal adaptation is difficult, but doable. And maybe Ryan will tell us some more.
Yeah, absolutely. That was a great setup. Thank you, Julie. You can just have the next slide. So I'm going to be talking today about the Canadian housing. This is basically looking at what we can do to help households. Awareness is one. Please.
You lost audio?
Yeah. Hey, Ryan, I think we're having, there we go.
Oh, okay, we're back.
It's back. It's a bit loud and choppy, but
Oh, okay. Hopefully it settles out a bit.
Right.
Yeah, just next slide, please. So I'm going to talk about the Chirp mobile app. This is basically trying to put information directly into the hands of residents so that they can prepare for a local emergency, whatever that looks like. What we know from our studies is that most Canadian households are ill-prepared to respond to a disaster effect that's affecting their homes or their communities. And while most communities do have information about local hazards on their websites and plans for future disasters, it's the communicating that information to residents in a meaningful manner that is often a challenge. Are we still having audio issues? Yeah? Okay, hold on. Is that going to be any better? Okay, going to be one of those days. Apologies, guys. Our team partnered with several Vancouver Island communities to help design, develop, and pilot a mobile app to help their residents to learn about, prepare for, and respond to identified local hazards. You can just have the next slide, please. That helps us to kind of remove some of the uncertainty that surrounds whether a home is at risk from a particular disaster or not. So what we know is that after a close call tsunami warning that we had in 2018, residents evacuating their homes at 3 a.m. faced a number of different problems. And we actually spoke with them door to door in Port Alberni to figure out what some of those issues were, what the barriers they faced were. We discovered about 18% of those households were either unsure or incorrect if their home was located in the inundation zone. And also we had some issues surrounding ideas about clear signage, whether there was, appropriate mapping for that particular area. But what we do know is that the city has prepared maps and provided those to the residents. Based on our discussions with the residents, it was clear we needed a better system and we needed one that could be accessible to everyone. Next slide, please. We partnered with a number of communities on Vancouver Island to kind of set that forward for us. So we looked from the small village of Tassis all the way to the city of Nanaimo to figure out what it was that those communities needed, what challenges they were facing in their communications that we might be able to address. And together we came up with a basic template of information about local hazard risks that their residents would basically need to be able to prepare for those risks and to help them to prepare for that in the future. Next slide, please. So what we see here is that we currently have 11 profiles. These are for hazards that are relevant to Vancouver Island context. We definitely have more coming down the line as well. Each profile provides kind of a local look at that risk in their own community. That includes things like an expert summary of that, a household risk assessment, a national overview of a hazard risk, and then a detailed description for their own community. And where data exists with much more detail, for example, the flood and tsunami risk that was just done in the district of Tofino, we're able to provide household level risk assessments based on that information, the studies that Julie was just talking about, helping residents to understand that hazard risk at the household level. And where warning and notification systems exist, we also connect them with those sources as well so that they can register to receive that information in the event of an emergency. Next slide. The kind of last piece of this puzzle is what households are actually doing and what they're made up of, because we can't just tell them what to do in the event of an emergency without knowing a little bit about them. So what we do is we kind of collect information about each user's home, their vehicles, family members, pets, to determine from our database of hundreds of potential response or preparedness actions, which are going to be best suited to their own needs. Some of the samples of things that we look at are broad age categories, disabilities, mental and other health conditions, assistive aids like hearing aids, LGBTQ status, and recent immigrant status. And for those working here as well, undergraduate and graduate students. Privacy is paramount, and I'd be happy to talk about that a little bit more detail down the road. Next slide, please. All of these three parts come together. The kind of hazard risk mapping Julie was just talking about, our database of potential actions, and the community pieces all on users' devices so that we help them to develop a customized preparedness and response plan unique to their home and the hazards they're going to be facing. So that if you have children, we put actions in for children. If you don't, we don't put those in. And if you're in the tsunami zone, we add tsunami-related hazards and take those out if you're not in such a zone. Next slide, please. We're going to be launching in 6 of our 7 pilot communities starting in coming weeks. Basically, what we're looking to do is to coordinate as a program to put this information out there to educate users about that risk and to also get it into the hands of users. That'll be starting in the village of Tassos and the district of Tofino and then rolling out to our other communities down the road. And in our phase 2, which will be coming up later this year, we're looking at expanding that to an Android version of the app. Right now, we're only on iOS devices. Also looking at more communities here in BC and also all the way across the country. And finally, just adding in some new hazards that'll be coming down the pipe. We want communities starting at the residential level to be as independent as they can be and ready to respond in the event of an emergency. Thank you all for your time. Can't wait to talk to you a little more later.
And people hear me? Great. So I'm Kevin, and I guess I'm the third speaker. And today I'm also the postdoctoral researcher at the Chemical and Biological Engineering Department. And today I will be sharing a bit about my project called Takachar, where we are using sort of trash to cash closed loop to build self-sufficient rural bioeconomies. Next slide, please. So biomass, so these are crop and forest residues, often are very promising as feedstock, renewable feedstock for different types of chemicals, fertilizers, and biofuel. But currently, most of the current conversion process, next slide, please, are very large scale and centralized. And for that to happen, the biomass must first be collected. Next. And collecting this loose, wet, and bulky biomass is a very costly process. And as such, many rural communities are often shut out from the bioeconomy because it's too logistically expensive for them to utilize that. And the only recourse then is to burn the residues in the field, which often can create a lot of pollution. And in some cases, catastrophic wildfires, especially along the West Coast. Next, please. So, and for example, in the summer 2020, Vancouver was actually ranked along with other West Coast cities as having one of the worst kind of air quality indexes in the world. Next slide. So what we are developing small-scale, low-cost portable systems that can latch onto the back of tractors and pickup trucks, and that can essentially travel from farm to farm or to rural forested landings to locally process and upgrade the residues on site into higher value customizable bioproducts, whether that's fertilizers, biofuels, or more specialized chemicals. Next slide. And this is something which we have built various iterations over the past few years, first in the lab and now sort of in the pre-commercial prototype testing moving to the field. Next slide. And the idea is that different types of biomass can then be deployed, through our fleet of reactors. Next. And once we, next please. And these reactors are actually in communication with sort of our cloud server. And next, when we know the market conditions, we can then coordinate these reactors to produce customized products that can coordinate sort of optimize to the local bioproduct needs and consumption requirements. Next slide. So in our first kind of application, we sort of started with kind of a rural smallholder farmer. So with people like Mrs. Wasicilia, who sort of plots in a 1 acre farm. And for her, one of the biggest problem is actually a lot of the fertilizer being produced from very far away and imported, which means that she's paying 2 to 5 times the world price for that. And because of her limited cash, she can often only afford the cheapest synthetic varieties that end up degrading and acidifying her soil. Next slide. So in this context, what we found was that the biochar-based fertilizer that's produced from our process compared to the status quo, which is chemical fertilizers, is that at the same price that the farmers are paying, we have increased their yields on average by 27% and net income by 50%, and not to mention the carbon sequestration and removal through intercepting that carbon from the plant into the biochar and then sequestering that into the soil for hundreds of years. Next slide. And here's what some of the farmers have to say. You may not hear it, but you can read the caption. Next slide, please. So far, we've managed to scale our initial pilot to around 5,000 farmers and created about 800K in real livelihood, and at the same time recycled about 10,000 pounds of waste and also removed that much CO2 equivalent. And as we scale, we anticipate this can also scale to wildfire-prone regions in terms of more efficient and effective vegetation management, and in reducing that wildfire risk, also reduce air pollution and potentially improving the power reliability in rural communities. Next. And finally, there's also a climate justice angle, because a lot of the carbon-based fertilizer we produce, next, is sequestering carbon. And next, also by avoiding the burning of the residues, and next, and also avoiding the transportation of this chemical fertilizers. Next, also avoids additional carbon. Next. And for this, there are many buyers, both private and next, in the sort of the carbon offset market that we can actually access. Next. And through our platform, we can actually distribute that next to the rural farmers. Next, sort of in a decentralized way through kind of a QR code verification. And this therefore delivers the carbon payment to those who actually are in the most marginalized societies. Next slide. And that's not only applicable in kind of the most poorest regions, but also has applicability here in the West Coast. Recently, we just started our kind of woody biomass trial, in this case, in one of the forests on the West Coast. We just built a prototype there. And as you can see from this video, are testing that out with the different woody residues that we can get in terms of vegetation management. Yeah, next slide. And that's all. And so I'll stop here and hope that you share our vision of turning trash into cash.
Hi, everyone. My name is Idalia Machuca. I graduated from the ES department a couple of years back in 2019 with Susan Allen. I did a master's in physical oceanography. And since then, I've been working with a company called Principal Power based in the San Francisco Bay Area as a mid-ocean engineer. And as of the last couple of weeks, I'm actually transitioning into a different company in a different type of position. And given that at the start of my industry career, I wasn't familiar with the term mid-ocean, I'm here to explain a little bit about what that discipline looks like in the industry and what people with our background and interests do within this industry. Next slide. Okay, so offshore wind is one of the key up and coming players in the energy transition for a future with sources of energy that are sustainable, hopefully soon more affordable and accessible. So a lot of people, most people that I talk to are most familiar with the land-based wind turbines and wind farms. Maybe they've been on road trips and they've seen it out the window. I recently saw a wind farm on a car commercial on TV. I was so happy to see that Coca-Cola actually did an ad where the worker comes back home and does this treacherous journey back home for Christmas, and it showed an offshore wind farm, and I felt noticed. So that was awesome. And the reason for getting excited to have a little bit of visibility on this industry is because what you can see on the map that's on this slide, if you look at the bar charts for the different regions of the world, in blue, you'll see the current installations. And so you're seeing that the dominant markets are Europe and Asia. And currently we only have about 35 gigawatts installed globally. And to put that into perspective, the International Renewable Energy Agency says that it will require about 2,000 gigawatts to be installed by 2050 to hit the 1.5 degrees Celsius climate target. So we have a pretty long way to go. But good news as of a few days ago was that BOEM, which is the Bureau of Ocean Energy Management in the US, has announced that there's going to be new leases. So something that was interesting to me getting into this industry was that you can have leases of areas in the ocean for energy developers to come in, build wind farms, and then decommission them after, let's say, 25 or so years. So there will be some ocean leases, which will be about 5.6 to 7 gigawatts of offshore wind energy, enough to power nearly 2 million homes. And yeah, we're foreseeing some growth in the industry. Yeah, but there's still a long way to go. Now into the role that we as atmospheric scientists and oceanographers take. Next slide. So metocean specialists within the industry study and characterize winds, waves, currents, tides, storm surge, and extreme events, the effects of extreme events like earthquakes, hurricanes, tsunamis, typhoons, which are the same as hurricanes, just different locations. And this is because energy developers need to understand what these metocean conditions are like in order to model the forces that will be impacting the offshore structures, because you don't want the offshore structure to sink or topple over, or you don't want to endanger your personnel during operations. So metocean specialists are involved in every stage of the project lifecycle. So you're looking at planning, assessing the resources available at a project site, design, transportation and installation, operation and maintenance, and then the final decommissioning. Next slide. Okay, so because this is a varied, you need varied outputs for the project lifecycle. Metocean specialists use different methods and data collection, all of which I think we're all familiar with. So a lot of the key processes that you're looking at, say, for example, wind speeds, wind directionality, locally generated waves, remotely generated waves, which are swell waves coming in. So different project sites are more affected by some of these parameters than others. Currents, water levels, and this is all done either by in situ measurements, satellite observations, forecasts, hindcasts. The dream is to have a nowcast for operations, live operations. And that's just one part of it. And once all of the data has been collected, then the really computational work continues in order to derive criteria, for example, for normal day-to-day operations, extreme events, weather windows for operations, and the inputs that will be used by the hydroaerodynamic engineers to take a look at how the turbine and how the structures respond to all the forcing around them. Next slide. Okay, so it's been an interesting experience to move maybe from a more academic sphere into this more financially driven, cost reducing world. And one of the main challenges right now is that the industry, as you saw from the map, is still quite young. So there's a lot of learning along the way, and a lot of decisions that seem cost reducing at first end up costing the project down the line. And this challenge could benefit from early and proper engagement with metocean expertise. So it's a constant struggle to advocate for the long-term security of the project through proper studies from the start. So for example, you want to get things started early so you have enough time to measure data. If you're doing a measurement campaign, usually you do measurements in conjunction with hindcasts. And then if you have sufficient time, then you can have more access, more quality control to the data, more quality control on the statistics. Should this not be done properly at the beginning due to resource constraints, then you end up having these costs down the line because there will be changes not only to the metocean, but then also trickle down changes into the design and engineering. And finally, because it's so young, we're still working with a lot of kind of like historical information rather than looking into the future, seeing, okay, well, this wind farm is going to be here for 25 to 30 years. What is climate change? How is it going to impact the different parameters that we are measuring as if they're going to remain constant? And also extreme events like hurricanes and tsunami are very loosely defined at the moment. So yeah, it's cool to be in this different application, and it's always nice to have this interaction with companies that are out there, teams formed by oceanographers and atmospheric scientists who have made this type of science into their own business, and they do all of these cool things out there within the industry world. Yeah, thank you. I'm looking forward to any questions.
Great. Good afternoon, everyone. I'm Greg Dipple. I'm known to many of you. For those who have not yet met, looking forward to getting back into the Earth Sciences building and EOS Main and South so that we can interact in person again. I'm a faculty member in EOAS, and I run a research group in carbon mineralization. Today, I just want to look at some longer time frame issues around climate change and research pathways towards developing and deploying technology to give us solutions. Next slide, please. This is a graph that probably many of you have seen. It shows emissions from fossil fuels and cement in billions of tons of CO2 per year, with some historical data and some projections. Really, the main take-home point here is that in the short term, we need to make these positively sloped lines and turn them into negatively sloped lines. Those are the short-term emissions that we need to do on a timescale of decades. And if we want to avoid the worst outcomes of climate change, we need to follow projections into the future along the blue lines, which would try and limit our warming to roughly 2 degrees centigrade. And by the turn of the century, that really is going to require, by the middle to the turn of the century, it's going to require that we actually are removing carbon dioxide from the atmosphere. We've already overshot our carbon budget, as if you will, for those scenarios. And so we ultimately have to get to negative, net negative carbon emissions globally. Next slide, please. So the problem is one of taking billions of tons of CO2 per year and putting them back into the oceans or the land or into rocks. And this seems like a profound problem, and it is. But there is hope. There are a number of technologies that are projected to be able to drive carbon removal from the atmosphere and putting them in short and long-term reservoirs at the scale of billions of tons for costs of on the order of 50 to a few hundred dollars per ton of CO2. So this plot on the left here shows 6 different technologies and some projections of what the consensus is today scientifically on where they might land in terms of capacity and cost. And on the right are some figures taken from the UN emissions gap report a few years ago that kind of illustrate how these processes work, if you will. On the right-hand side on the top, you can see there's burning a fossil fuel takes carbon from the geological reservoir and puts it into the atmosphere. In the 3 scenarios underneath that, we're taking carbon dioxide from the atmosphere and putting it either into the land through afforestation or agricultural practices, into the ocean through ocean alkalinization or fertilization, or into the geological reservoir through something that's typically termed enhanced weathering. And today I'd want to spend just a few minutes talking about our research project in enhanced weathering, specifically one aspect of that called carbon mineralization. Next slide, please. The real focus here is to emphasize how research collaborations with industry can drive technology development and deployment to build towards some of these long-term solutions that we need. Our project is really broken up into 3 groups. The group here at UBC, we have the main focus is to use ultramafic mine tailings to capture and mineralize CO2, thereby putting them into stable geological form, which has durability in the thousands to hundreds of thousands of years and beyond. So that's the main deployment. We call that SCOUT, for sequestration of CO2 and ultramafic tailings. A lot of work needs to be done to understand the best places to do that. Fundamentally, the reactivity of the tailings is driven by their mineralogy, and we have to take advantage of the heterogeneity and the geological diversity of the oceanic and continental crust in order to drive these processes. So there's a component that looks at understanding the best places to do it. That helps reduce the cost. And lastly, fundamentally, as Earth scientists, we're driven by using the planet to teach us how to do things. And so we study a number of natural analogs to get insights into how to drive this acceleration. Next slide, please. So this slide just shows some recent, images from some of the recent experiments we've been running. We run experiments at mine sites and in field environments. We run both capture of CO2 from flue gas, for example, from electricity generation at a mine site, but also for capture from air. The long-term pivot for the flue gas capture technologies are that ultimately one could run that with green diesel or biofuels and run sort of an equivalent of a BECCS, so a bioenergy capture, carbon capture storage type system. But also we can pair these technologies with direct air capture systems on site to use concentrated CO2 streams to drive mineralization. And it's, after about 15 years of doing research in this area and spending about $7 million, I think this year we might cross the threshold where we will have actually sequestered an entire ton of CO2. So that speaks to the profound issue of the scale of the problem, but we're on track to cross the 10-ton threshold this year, and our plans are to cross the 100-ton threshold within another year or 2 after that. So we are getting to the point where the cost will go down and the scale will go up. Next slide, please. Understanding the best places to do it is really important. So we have a project we call CAMP, Carbon Mineralization Potential. One example of that, the primary example of that is a project funded by Geoscience BC, where we used the existing geological, geochemical, and geophysical data sets for the province of British Columbia to map out where the best rocks were to do this work. And specifically, we're looking for specific mineral assemblages that have distinctive physical properties, which allow them to be imaged geophysically once we know we're in the right rock type. And the outcome of this work was that there's capacity to mineralize roughly 56 billion tons of CO2 in the near surface of the rocks of British Columbia. That's the top row in the table in the upper right there. So this is roughly 800 years worth of BC's entire emissions based on current emissions, which are about 70 million tons per year. Obviously, we're not going to do 56 billion tons within the province of British Columbia, but it speaks to the importance of understanding the size of the prize, where the potential is, and then choosing from sites within that where the processes can be run at scale at low cost. Next slide, please. Lastly, monitoring and verifying the stored carbon is really important, and we steal technology from other parts of earth science and agriculture and forestry. We work with Uli Meyer in this area where we're deploying dynamic closed chamber systems and eddy covariance systems to actually monitor CO2 uptake in our field experiments. These data are important both for optimizing the processes as well as for verifying the stored carbon. So to end with the last slide, I'd like to leave you with sort of an image of one example of where this can hopefully drive industry development. So these plots here show the tons of CO2 that we sequester per tons of tailings on an annual basis. The red plots show the CO2 emissions of mining activities because we're using mine waste in these technologies. And the different colors of red to pink really illustrate and emphasize that the greenhouse gas emissions associated with mining are split between haul or moving material around or truck emissions and electricity generation, which is used to run the mine. And the emphasis of the three red stacks on the left-hand side of the plot is that this is all for nickel deposits. Nickel are an important commodity that we need more of in order to transform our transportation sector into electric vehicles. The importance of this is that different types of nickel deposits have very different carbon emissions profiles. And so it's important to understand as we look at expanding or developing nickel mines, we need to understand those emissions profiles. And the green bars show the sequestration capacity or the mineralization capacity of the waste produced by those same types of mines. And the important point is if we marry the small red boxes to the large green boxes, we can essentially not only reduce or eliminate the carbon footprint of mining, we can actually mine and run in a carbon negative way. So that's kind of illustrated in the plot on the right. There's significant industry work underway to decarbonize, to deploy renewable energy for electricity generation at mine sites, including remote areas, and to decarbonize transportation within mining operations to dramatically reduce the size of the red bar. At the same time, if we do that mine development on the types of nickel deposits that can be mined at low cost in terms of energy and haulage, then they will have a low carbon footprint. We also want to focus that work on areas where the host rock, the waste, crushed waste or mine tailings that's used for carbon capture and storage is relatively high. So right now, most nickel mining is done in deposits that have very high red bars. They have high ecological and carbon footprints associated with their operations, and their host rocks are pretty poor in terms of their potential to sequester carbon. So we believe that the market forces that are currently driving the mining industry can help us to push the mine development towards deposit types where we can extract the nickel at low energy and low carbon cost, and at the same time, maximize the amount of carbon sequestration potential we can do at those mines. The end result of this will be carbon mines that do not produce emissions. They decarbonize the supply chain to batteries for electrical vehicle transport, but the sites will also produce a net removal of CO2 from the atmosphere, thus providing an environmental benefit. Hence the rather absurd sounding moniker of mining for the environment. And I'll leave it at that.
Thank you very much, Greg. So just before we dive into the discussion and questions, I'd like to ask Yoshi to give us a brief introduction to what next week's topic will be.
Yeah, hey everyone. Thanks, speakers. Those are some great talks, and I have some questions myself. So next week we have Dr. Catherine Hixson, who actually did her undergrad and PhD at UBC at this department, and is well known by many in the volcanology group here. She's been spending most of her career working on volcanology in academia, but then moved to the geothermal energy industry and has been a big proponent of geothermal energy. So next week she'll give a exciting talk giving us an overview of geothermal energy development around the world, but also the potential for it here in BC. So be next week, same time, January 27th on Zoom. I'll provide a link later in an email to everybody, and maybe in person if possible, but certainly on Zoom. So hope to see you then. Thanks. All right. So I want to start the question period. Colin, do you have a question for one of the speakers?
Yeah, I have a question for Idalia. I was just sort of curious about what's behind that, your 2,000 gigawatts of wind power target number. How much of that is sort of like, how much of that is driven by just what's needed in terms of renewable energy versus compared against availability of suitable sites with, say relatively reasonable impacts to, whether it's environment and shorebirds and things like that. I guess I'm just wondering how much of that 2,000 runs into other limitations imposed by, I guess, availability of sites.
Right. Yeah, that's, there is so much involved in just looking at energy production. So when, for example, when commercial professionals, like the more sales section of the business, when they speak about energy production, they go into power, because you don't really know how much energy can be produced by a wind farm, because you can't really predict with 100% certainty what the wind conditions are going to look like, and it's hard to foresee any limitations around performance and things going wrong in the wind farm. So for that 2,000 gigawatt estimate, I know that the report that spoke about that estimate took a look at all the different energy sectors and basically looked at what could be possible with each sector playing a role to reach that ultimate goal for reducing emissions sufficiently for the 1.5 degree target. I think it's actually called the net zero emissions target by 2050. But yeah, it's hard to say, but I think what they're going for is that 1,000 gigawatts this is what we need to reach that goal, all limitations considered. Yeah. Was that clear?
Yeah, I think so. Thank you.
Okay.
So I'll go ahead here. Maybe a question for Julie. I remember reading somewhere that the Netherlands was actually forcing people to move out of high risk, I think, flood areas and trying to reclaim some of that land to become floodplains. I'm not sure if I'm remembering it correctly, but they were also compensating people appropriately for the value of their land, but they weren't giving them a choice. So I think you touched upon that we may have to consider tough policy decisions like this moving forward. Do you think we should start discussing that and considering that here in Canada?
I'm not providing any commentary on federal government policies at the moment. Just kind of, it is happening in Canada. Grand Forks is actually an example of where a buyout program has been implemented. They have been considered, I'm not sure if implemented, both in Quebec and in Ontario. And there are a lot of conversations in Northern Arctic communities in Canada right now about community-driven relocation. So it is far from theoretical, even here in Canada. And the Dutch approach is typically called room for the river, is a way that they are sort of exporting those ideas and sharing those ideas. And it comes with a whole combination of different approaches, but some of them are ensuring that some areas are just saved as room for the river, and they're looking at combinations of retreat from very vulnerable areas, especially in Canada and BC. We have a lot of geomorphic hazard, and it's much harder to defend an area from a geomorphic hazard than it is from just water levels. So that's a higher risk part of the picture. But really it's about looking at all of the social and river and biological factors in an area and coming up with a plan, a long-term plan that makes sense to direct investment?
Thanks. I think David has a question now. Oh, you have to unmute. Still muted, David.
Yeah, I'm unmuted now, I think. I had a comment on Idalia and then a question for Ryan. I had much of my career in Utah, and there's a place in southern Utah where there's a wind farm, a solar farm, and a geothermal energy production that's produced about 40 megawatts continuously for the past 30 years. And the geothermal people, which is my area, were always a little bit annoyed that the wind and the solar people quote their energy in terms of installed production without regard to the performance, but the sun doesn't shine at nighttime and the wind doesn't blow all the time. And the typical wind performance is about 27% in the southern Utah deserts. And I just wondered whether Idalia could comment on what they are in the offshore regions. And then my question for Ryan was, you didn't talk about jurisdictions and responsibilities and whether that gets in the way of mitigation. There's a lot of talk in terms of the Lillooet fires and so forth, of what could the province do, what could the regional councils do, and what could the mayors in the individual villages and towns do. So maybe Idalia first.
Yeah, sure. So I'm not super sure about the most correct answer. Currently, what we're doing for offshore wind projects, the most recent projects that we're starting up, we're using the 14 megawatt turbines, which are the new, I think it's the NREL one. And you're looking at wind farms, the smallest ones are about maybe 10 turbines out in the wind farm, to, I think, one of them, I wouldn't want to misquote, but it's dozens. So yeah, I'm not super sure in the end what the energy production actually looks like, taking into account the beyond the capacity. But yeah, I'd have to look it up to be sure.
But
Yes, and go ahead, David.
does anybody else know this number? But if it's 25%, for example, then instead of talking about 15 megawatts, then then it's 1/5 of that, or 3 megawatts. It makes a big difference in terms of our target of production.
Yeah, and I think that goes in line with Colin's question too. I'm not super sure.
Maybe, if that's okay, if I can insert a follow-up question. I guess just in terms of the wind offshore, for a typical wind farm, maybe this isn't as simple of a question as possible, but how strong is the variability of the wind in terms of, is the turbine usually operating at peak performance, or are there long periods with low wind?
Yeah, that's actually a really helpful question. So when you're looking at the performance of the wind farm, there's something called a power curve. And as you, on the x-axis, you have wind speed, and then you have power production. And it basically goes kind of like, not exponential, but I'm not sure, it curves. And then there's a point where you hit that, it's called rated power. And at that point, you're producing the maximum possible power that that turbine has the capability of producing. Yeah, that feeds into this discussion that we're having, where you're not always going to have wind speeds at, say, 12 meters per second that hit right there at the rated power, and the turbine is just going at full capacity. So yeah, it like this whole conversation that we're talking about is narrowing down on what that probability looks like, that wind speed probability looks like at the site, in order to see, okay, well, you could have a capacity of this much, right? Let's say the 30 gigawatts or something like that. But how often are you reaching that rated power zone that you're actually producing that much. I would say the most political answer I could give would be, it depends for every site. But I don't know how much of that is incorporated in the final numbers that we're advertising. And I'm not advertising it. I just do the meadow share.
Just to address the jurisdiction issue that David had there. Anytime we're dealing with resilience, we have multiple layers of overlapping jurisdictional issues going on there. What we're doing with CHIRP is we're kind of circumventing those, but we're directly dealing with our community partners. So we partner specifically with one community using their resources and their communication channels for that. And we then target their residents. So we are doing this on a per community basis, which means it's a lot of legwork on our end because we have to do this for each community, and each community is slightly different. But the end result is we're getting targeted right at the residents in a way that is relevant to the planning that's already being conducted in the community. We already know the studies that they've already done in that community, and we can use the best data that we have available for us. I think that one issue we have in Canada is that risk data is not particularly good in some areas, and it's definitely not consistent from place to place. So we have to build those out on a per community basis. And since we have to do that anyways, we might as well just work directly with the communities and let them deal with those higher level authorities.
Thank you.
Thanks.
Mark?
Yeah, thanks. It was a nice series of talks, everyone. My question is to Idalia, but perhaps it's useful in any discussion of alternative energy. I used to work with someone who designed wind turbines, and one of the biggest challenges in selling that technology at least 25 years ago was the dissipation in the power curves. So basically bearings wear out, machinery dies, and everything gets a lot worse as soon as you put it offshore and salt breeze in the ocean. So some of the discussions that I watched and was slightly involved in there, before 2010, were balancing the cost of putting in some of these systems with their useful life. So has the useful life now become such that we don't have to worry about usually the very large costs up front? Or is the power curve and its decay over time really still a problem?
Oh, it's still a problem. I think it's a whole subfield within the industry to look at they call it the LCOE, the levelized cost of energy. And it's a formula that takes into account all those things. So it's not resolved from what I've seen. So I'm not doing the like actual modeling on the turbines or on the platform, but I don't think we are quite at the point that we're looking, at least not for the platform, at that dissipation of the power curve, because actually, all of this discussion is helping me understand what I do even more. So I work for the company that builds the semi-submersible platform, not the wind turbines. And so then the wind turbines are then integrated on the platform and then installed offshore. So I'm not super sure what goes on the wind turbine side of things. But what is interesting is I really haven't heard all that much discussion in my company with regards to how the platform will also respond to whatever differences during the life cycle of the turbine itself, the turbine that is mounted on the platform. But from what I'm seeing from presentations that I've seen from the commercial teams is that this is still an ongoing discussion, and different labs are still looking into this question.
I'll just jump in and say we recognize it's 5 p.m. If some folks have to leave, that's okay. But for the rest that want to keep discussing, please feel free. The host of the Zoom will stay on to keep the fire going. So David, you have a question?
One more question of Greg. He showed a slide, really interesting slide of emissions and where we need to do to get down to zero emissions. And I'm interested in that slide. It's zero is net negative. And I wonder if that takes into account the roughly 5 gigatons of natural sinks in the oceans and the lands.
Yeah, if you're referring to the very first slide, those are basically out of the IPCC reports. That's an early version. There's some more recent ones, and those are looking at a global scale with different modeling scenarios, how much of our emissions we need to reduce or how much we need to go net negative, and then how that affects the total CO2 in the atmosphere, which of course has all the natural pathways as well. So that plot specifically is some specific anthropogenic emissions and how much we need to reduce them such that the impact on the larger carbon cycle leads us to certain warming scenarios. So the short answer is yes, it includes those natural processes.
But the axis has 0 gigatons.
Those and the units, it's emissions from fossil fuel and cement only. So it's not even land use change emissions and other things. Okay. It's specifically around what we have to do to reduce or offset in terms of industrial emissions around specifically fossil fuel use and cement production.
Right. I think we saw the same slide last week, and the comment was we have to get below 0 on emissions, but in fact that doesn't take into account the roughly the natural absorption in the oceans and then the land, the biosphere that takes it in. And I think we're now producing roughly 10 megatons of carbon dioxide per year, but the land use in the oceans absorb 5 gigatons.
Yeah, so that's included in the models that are the warming scenarios. And part of the issue is once we start actually reducing the concentration of CO2 in the atmosphere, some of those natural processes will ultimately reverse. And the long-term models take that into account.
Okay, thank you.
Yeah.
Yeah, Ryan, you have a question?
Yeah, also for Greg, I think this is great what's happening in the mining field, but what's the next frontier after mining? Like, where does this apply in the next steps?
Yeah, our work in mine tailings is only one small piece of carbon mineralization, which is only one part of enhanced weathering, which is one of the 6 boxes that were on that diagram. So we're not even a piece of pie, we're a flake of crust, if you will, on that larger thing. In terms of mining at a large scale, what can that contribute? Keep in mind we're trying to get to removals on the scale of perhaps 10 gigatons per year ultimately by the turn of the century. If you eyeball some of those curves, at the if the technology works well and is deployed globally, then specifically mine tailings carbon mineralization could contribute at the scale of probably a couple 100 million tons per year, so much less than a gigaton. If the mining scenarios of a lot more mining driven around copper, nickel, cobalt type needs for renewable energy and electrification of the transport sector, some of the most dramatic extrapolations or predictions for what's needed in terms of metal production could drive that number to a gigaton. So the most optimistic scenario in terms of scale would be that mine-based carbon dioxide removal might hit a gigaton ultimately, but implicit with that is a lot of mining, which is a significant issue. One of the challenges are that for us to electrify the transportation sector, we need to be supplying more nickel than has been mined historically in the history of the human race. That could change as battery technology evolves, but there are going to be metal needs. And I think in a couple of weeks or in a few weeks, John Steen and others will be speaking on that topic specifically. But there are other technologies around carbon, around enhanced weathering, include some of the things you read about with spreading crushed basalt on fields in Illinois. There's some large scale experiments there. There's a company called Future Forests that's sprinkling crushed basalt in forests in Scotland. There's companies that are putting olivine in the ocean to drive reduction in ocean acidity and drive carbon uptake through the ocean pathways. There's a number of different there's many other aspects of enhanced weathering and carbon mineralization beyond our work specifically.
I have a question for Idalia. I've heard that many offshore wind farms, particularly in the Atlantic, I think, and on the East Coast, I have colleagues in the industry there. They're talking about developing on-site hydrogen fuel production using the energy from those wind farms and then using that as a means of storage and then transport back to, say, the mainlands. Is this a common push across the industry, or mostly just a few companies?
I don't think it's that common yet. Where I've been working, we've had quite a few projects. Only one of those projects has had that work scope included, the hydrogen, I don't know, something with hydrogen. So the way in which we incorporated that part is including accommodations for it on the platform structurally. But I mean, we don't really get into the science of it. But yeah, it's not that common. I remember when I first interviewed for this company, I even mentioned something as simple as I imagine that all of these turbines, they must have sensors on them, and this would be cool for coming from an oceanography background. I'm thinking that anything that's on the ocean should have some form of measurement instrument on it. And I was surprised to see that, no, that's not actually common at all. So yeah, it's still way at the beginning, I feel. There's still a long way to go in terms of really taking advantage of these wind farms.
Well, we are 8 minutes past 5. I don't want to hold the speakers too much longer. If nobody has any burning questions, I think we can end it there. And please give one more round of applause to our amazing speakers. I really enjoyed all the presentations and the talks and some of the exciting work on apps and whatnot, mitigation that I heard of. It was great. Thank you.
Thank you.
All right. See you next week, everyone.
Thanks.
That's good.
Bye.
Thanks, Catherine and Birgit, for putting that one together. It was great.
Yeah, great job.
Thank you all.